Welcome to Softly Curious. There is a place beneath your feet right now, not deep, not dramatic, just a few meters down, where the air has not moved in centuries, where the temperature has held the same number, degree by degree, through ice ages and heat waves and every season that has ever passed above, where water moves so slowly through stone that a single drop takes 1,000 years to reach the floor. You have never seen this place. Almost no one has. And yet, it is there, waiting, the way things that are very old and very patient tend to wait. Caves are among the oldest structures on Earth that no human hand has ever built or touched. They form without intention, without design, without anyone deciding they should exist. And yet they arrive hollow, dark, and extraordinarily precise, as though the planet has been quietly making rooms for itself all along. The most common kind of cave begins with limestone, a rock that seems solid and final, but is, in geological terms, remarkably willing to dissolve. Limestone is made largely of calcium carbonate, the same mineral that builds coral reefs and seashells, and the white cliffs that line certain coastlines. When rainwater falls through the atmosphere, it picks up carbon dioxide and becomes slightly acidic. Not dangerously so, not even noticeably so, but enough. Enough, over time, to eat through rock. This process is called karstification, and it is one of the slowest and most consequential chemical reactions in the natural world. Water finds a crack. It widens the crack. It follows the crack downward and sideways and deeper, dissolving the rock as it goes, removing material grain by grain, century by century, until one day, though day is not quite the right word, there is nothing left in a particular place except space. That space is a cave. The timescales involved are almost impossible to hold in the mind. A passage the width of a human hand might take 50,000 years to form. A chamber large enough to park a commercial aircraft might require several million. The Mammoth Cave system in Kentucky, the longest known cave system in the world at over 650 kilometers of mapped passage, has been forming for roughly 10 million years. Every corridor, every room, every low tunnel that a modern explorer must crawl through on their stomach, all of it carved by water, by chemistry, by time doing what time does when nothing interrupts it. Limestone caves are the most numerous, but they are not the only kind. Lava tubes form when volcanic rock flows downhill, and the outer surface cools and hardens while the molten interior continues moving. Eventually, the interior drains entirely and leaves behind a long, smooth-walled tunnel, sometimes kilometers long, sometimes wide enough to walk through upright without ducking. These tubes can form in days or weeks, a geological instant compared to the slow dissolution of limestone. The Kazumura Cave in Hawaii is the longest known lava tube in the world, stretching more than 65 kilometers, most of it formed in a single eruptive event. Sea caves form differently again, where waves strike a cliff face repeatedly, targeting cracks and weaknesses in the rock. The mechanical force of the water gradually hollows out a chamber. Unlike dissolution caves, sea caves grow through physical erosion. The rock does not dissolve so much as it is physically knocked away, piece by piece, over centuries of tidal rhythm. Many sea caves remain accessible only at low tide or only from the water, giving them a particular quality of hiddenness. They are caves that must be earned. And then there are glacier caves, which form within ice rather than rock, shaped by meltwater moving through a glacier's interior. These are caves that move slowly, as the glacier itself moves, a hollow space migrating across a landscape, existing for a few decades before the ice shifts or melts and closes it again. What unites all these formations, regardless of how they came to exist, is darkness. Not the darkness of a room with the curtains closed, or a hallway with the lights off, a darkness that is total, absolute, and ancient. In a cave beyond the reach of natural light, a human hand held inches from the face is completely invisible. This darkness shapes everything inside a cave. It shapes the temperature, which stabilizes at roughly the mean annual temperature of the region above. Cold enough in northern systems to require warm clothing even in summer, mild enough in tropical caves to feel almost comfortable. It shapes the humidity, which in most caves sits near 100%, the air so saturated with moisture that surfaces glisten and the breath of a visitor briefly clouds in front of them. It shapes the sound, which in large chambers takes on a particular quality of depth and echo, and in narrow passages becomes something closer to silence than most people have ever experienced. The air in a deep cave is also ancient in a way that is not obvious at first. Because cave systems are largely sealed from the outside atmosphere, the air circulates slowly, if at all. In some chambers, the same air has been sitting undisturbed for thousands of years, breathed by no mammal, stirred by no wind, changed by nothing. When researchers enter certain remote cave chambers for the first time, they are, in a very real sense, breathing air that has never been breathed before. This is part of what makes caves so difficult to fully grasp. They are not simply holes in the ground. They are environments with their own physics, their own chemistry, their own time. They predate every civilization, every species, almost every mountain range currently visible on the surface of the Earth. They are spaces that formed before there was anyone to enter them, and that have waited, unchanged and undisturbed ever since. The world beneath the surface is far larger than most people realize. Scientists estimate that roughly 20% of Earth's land surface sits above karst terrain, ground that is, somewhere underneath, riddled with cave systems. Most of those systems have never been entered. Many have never been found. The caves that human explorers have mapped in detail represent only a fraction of what exists, and every year, in mountain ranges and forests and remote plateaus across every continent, new passages are discovered, new rooms, new corridors, new spaces that the planet has been keeping to itself for millions of years. Somewhere beneath you, in all likelihood, the process is still continuing. Water is moving through a hairline crack in limestone right now, dissolving the rock one molecule at a time, slowly making a room that no one will enter for another 50,000 years. A cave does not simply exist. It breathes, not in the way a living thing breathes, not with lungs or rhythm or intention, but with a slow, continuous exchange that most visitors never notice, and that took scientists a surprisingly long time to fully understand. Air moves through cave systems in response to temperature differences between the cave interior and the surface above. In winter, when outside air is colder and denser than the air inside the cave, cold air sinks into lower entrances and pushes warmer cave air out through higher openings. In summer, the process reverses. The cave exhales in one season and inhales in the next, and this cycle has been running uninterrupted for as long as the cave has had openings to the surface. Some caves make this breathing audible. At certain entrances, particularly narrow ones, the pressure difference between interior and exterior air creates a wind, sometimes gentle, sometimes strong enough to blow a hat from someone's head. These blowing caves have been known to local communities for centuries, sometimes regarded as sacred, sometimes simply useful. In hot climates, the cool air flowing from a cave entrance in summer offered a reliable form of natural refrigeration. In parts of Europe, cave entrances with consistent airflow were used to store food long before mechanical cooling existed. The temperature inside a cave is one of its most reliable features. Deep within a system, far from any entrance, the temperature stabilizes at approximately the mean annual surface temperature of the region. Not the summer average, not the winter average, but the average across the entire year. In Kentucky, where Mammoth Cave sits, that means a constant 12 degrees Celsius regardless of the season above. In the caves of southern France, it is closer to 13. In tropical systems, the stable temperature can feel warm and almost humid. This consistency is not accidental. It is a direct consequence of the cave's insulation from surface weather. Rock is an excellent thermal buffer, and enough of it, stacked above a cave passage, blocks every fluctuation that happens above. This thermal stability has made caves extraordinarily valuable as scientific instruments. The stalactites and stalagmites that grow inside them, those slow mineral formations dripping from ceiling to floor, record climate. History the way trees record it in their rings, but across far longer timescales. Each layer of mineral deposited in a cave formation contains chemical signatures of the rainfall and temperature conditions at the time it was laid down. Researchers drill into these formations and read the layers backward through time, reconstructing climate conditions from tens of thousands of years ago with remarkable precision. A stalagmite from a cave in China might contain detailed records of monsoon patterns going back 300,000 years. A formation from a cave in South Africa might preserve evidence of rainfall shifts that correlate with human migration routes out of the continent. Caves, in this sense, are archives, not of written language or human memory, but of atmospheric chemistry and hydrological cycles, kept in stone and perfectly preserved. The water that creates caves does not stop working once the cave exists. It continues to move through the system, and as it does, it deposits the very minerals it has dissolved elsewhere. This is how cave formations grow, not by accumulating material from outside, but by the cave itself slowly reconstructing, in a different form, what was once solid rock. The water that carved a passage over 1,000,000 years may spend the next 1,000,000 years decorating that same passage with crystalline structures of extraordinary delicacy. The cave simultaneously destroys and creates, dissolves and builds, in a process that has no beginning and no planned end. Humidity is the other constant. In most cave systems, the air holds moisture at or near saturation, close to 100% relative humidity, because the water that moves through the rock constantly evaporates into the enclosed air. This means that surfaces inside a cave are rarely dry. Walls glisten. Floors hold thin films of water. The formations that grow from ceilings are perpetually wet, their surfaces alive, with the slow movement of mineral-laden water working its way toward the tip, where it will either fall to the floor or evaporate and leave behind another invisible layer of calcite. That layer might be a fraction of a millimeter thick. It might represent a century of growth. In caves where water flow is particularly slow, a single centimeter of stalactite can represent 1,000 years of accumulation. What this humidity does to sound is something that first-time cave visitors often remark upon. In a chamber with high ceilings and wet walls, sound behaves differently than it does in any constructed space. Voices carry in unexpected directions. Echoes arrive from angles that don't seem geometrically possible. Water dripping from a formation 20 meters away can sound close enough to touch. Some large cave chambers have acoustic properties so unusual that sound engineers and musicians have sought them out deliberately. A few cave systems have hosted concerts, specifically because of the way the space transforms and extends sound, wrapping it in a reverb that no artificial room can quite replicate. The relationship between a cave and the landscape above it is closer than it appears. Rainwater that falls on the surface above a cave system often reaches the cave relatively quickly, within days or weeks in active systems, carrying with it whatever it has picked up along the way. Agricultural chemicals applied to fields above a cave can appear in cave water within a single rainy season. Pollution from roads or industrial sites can travel underground and emerge in cave springs kilometers away. The cave is not separate from the surface world. It is connected to it through thousands of invisible pathways, receiving everything the surface sends downward and filtering it, slowly, through rock. This connection runs in both directions. The springs that emerge from cave systems supply drinking water to hundreds of millions of people worldwide. Many rivers that appear to begin at a spring are in fact continuing a journey that started kilometers away on the surface, went underground through a cave system, and then re-emerged. The water flowing from a spring in a French village might have fallen as rain on a hillside several kilometers away, disappeared into a sinkhole, traveled underground through passages no human has ever entered, and arrived at the spring after a journey lasting weeks or months. The cave, then, is not an isolated underworld. It is a working part of the planet's hydrology, its climate record, its thermal architecture. It is a space that is simultaneously ancient and active, formed over millions of years, but still changing, still breathing, still receiving the rain that falls today and sending it forward, quietly, into the future. Life does not require light. This is one of the more unsettling conclusions that biology arrived at slowly, reluctantly, over the course of the 20th century. Unsettling not because it is frightening, but because it dismantles something that seemed fundamental. Light drives photosynthesis. Photosynthesis drives the food chain. The food chain sustains almost everything alive on the surface of the earth. Remove the light, and the logic appears to collapse. And yet, in caves around the world, in passages where no photon has ever reached, life continues, patient, adapted, and in many cases thriving. The organisms that live in caves are classified by how deeply they depend on that environment. The distinction matters because it reveals something about the relationship between a species and darkness, whether darkness is something it tolerates, something it prefers, or something it can no longer live without. The first category is the troglodytes. These are animals that use caves, but do not complete their entire life cycle inside them. Bats are the most familiar example. They roost in caves during the day or through winter, but they leave to feed, to migrate, to interact with the outside world. Bears have historically used caves for hibernation. Certain birds nest in cave entrances. The troglodyte treats the cave as shelter, a resource among many, and retains its connection to the surface. It brings energy into the cave in the form of droppings and organic material, feeding other organisms that never leave, and in doing so, acts as a kind of courier between the two worlds. The second category is the troglophile. These species can live either inside or outside caves, but show a clear preference for the cave environment. They have begun adapting. Their eyes may be slightly reduced, their pigmentation slightly faded, but they are not yet committed. Given the right conditions, a troglophile can survive on the surface. Given a cave, it will usually choose the cave. Certain salamanders, spiders, and beetles fall into this category. They occupy the middle ground, neither fully of the surface nor fully of the dark, and they offer a glimpse of what adaptation looks like in the middle of the process rather than at its end. The third category is the troglobite, and this is where the story becomes genuinely extraordinary. Troglobites are obligate cave dwellers, species that have adapted so completely to cave life that they can no longer survive outside it. They are born in darkness, live in darkness, and die in darkness. And over thousands of generations of cave existence, their bodies have been shaped by that fact in ways that are immediately visible and sometimes startling. The most obvious adaptation is the loss of eyes. In an environment where there is no light whatsoever, eyes are not merely useless, they are metabolically expensive. Building and maintaining eyes requires energy and resources. And if those eyes return no information, natural selection quietly stops investing in them. In troglobites, this process plays out across generations. Eyes become smaller, the optic nerve reduces, the structures that once supported vision gradually disappear. In many species, the eye socket remains as an anatomical ghost, a shallow depression where an eye once was, but the eye itself is gone. What was once a sense organ becomes, over deep time, an absence. Pigmentation follows the same logic. Color in animals serves multiple purposes: camouflage, signaling UV protection, but all of these functions depend on light. In a cave, there is nothing to hide from, no signal that color can send, no ultraviolet radiation to block. The genes responsible for producing melanin, the pigment that gives skin and scales and shells their color, gradually become inactive across generations. The result is animals of an almost translucent pallor, white crayfish, colorless fish, pale spiders. That look, to a surface dweller's eye, somehow unfinished, as though the planet ran out of paint before it got to them. But the cave does not simply take things away. It also builds. The same selective pressure that reduces unnecessary senses amplifies those that remain. Cave fish that have lost their eyes typically show dramatic enhancement of their lateral line system, a sensory organ that detects vibrations and pressure changes in water. Where vision once mapped the environment, mechanoreception now does the same job with greater sensitivity. Certain cave insects develop antennae that are extraordinarily long relative to their body size, capable of detecting the faintest air movements. Cave spiders build webs tuned to the specific air currents of their particular passage. The cave, depriving its residents of light, forces a reorganization of the sensory world, and the organisms that survive that reorganization often emerge with capabilities that surface-dwelling relatives simply do not have. Metabolism slows as well. Food is scarce in caves. The organic material that sustains cave ecosystems arrives largely from outside, carried in by water, by trogloxines, by the slow infiltration of surface nutrients through the rock. It arrives irregularly and in small quantities. Cave-adapted animals have responded by becoming extraordinarily efficient, slowing their heart rates, reducing their activity, extending the time between feeding events to a degree that would constitute starvation in a surface species. The alm, a blind cave salamander found in the karst systems of the Western Balkans, can survive without food for up to 10 years. It may live for a century. Its entire biological strategy is built around patience, waiting for energy to arrive, using as little as possible in the meantime, and persisting across timescales that most vertebrates never approach. The alm was first described scientifically in the 17th century, when specimens washed out of cave springs in Slovenia following heavy rains. Local people had known it for centuries and called it the human fish, a name that captures something real about its appearance. It is long and pale and moves with a slow, deliberate grace that seems almost considered. Its forelimbs are thin and delicate, its head slightly flattened, its vestigial eyes visible beneath the skin as faint, dark spots. It breathes through both lungs and external gills, a combination that gives it flexibility in the variable oxygen conditions of cave water. In captivity, alms have lived past 70 years with no apparent signs of aging. In the wild, protected within the darkness of Balkan karst, they may live considerably longer. The cave does not make life easy. It removes light, limits food, restricts movement, and creates conditions that would be hostile to most surface species. But for the organisms that have committed to it, that have, over thousands of generations, traded their eyes for sensitivity and their speed for patience, it offers something the surface cannot: stability. The temperature does not change. The weather does not reach them. The predators that hunt by sight cannot function here. The cave, in its darkness, turns out to be one of the most stable environments on the planet, and stability, for the right kind of life, is its own kind of abundance. Below the animals, below the roots and the insects, and the pale fish drifting through underground rivers, there is another layer of life, one that operates without any of the inputs that surface biology takes for granted. No sunlight, no photosynthesis, no organic material falling from above. Just rock, water, and chemistry. And within that stripped-down set of conditions, life not only exists, but has built something that functions in its own quiet way, like an ecosystem. The organisms responsible are bacteria, not a single species, but entire communities of them, living on the surfaces of cave walls, in the thin films of water that coat formations, in the sediment of underground pools. Many of these bacteria are chemolithotrophes, a term that means essentially rock eaters. This process, chemosynthesis, as opposed to photosynthesis, was once considered a biological curiosity, a footnote in microbiology. The discovery of hydrothermal vent communities on the deep ocean floor in the late 1970s changed that assessment entirely. Suddenly, here was an entire ecosystem: shrimp, tube worms, crabs, fish, sustained not by sunlight, but by chemical energy rising from the Earth's interior. Cave systems offered a parallel revelation on land. In Mammoth Cave in Romania, sealed from the surface for approximately 5 million years, researchers in 1986 discovered a fully functioning ecosystem built entirely on chemosynthesis. The cave contains a layer of hydrogen sulfide-rich water at its base, and sulfur-oxidizing bacteria form the foundation of a food web that includes 48 species found nowhere else on Earth: spiders, leeches, water scorpions, isopods, all of them adapted to a world that has been in complete darkness and complete isolation since before modern humans existed. Mammoth Cave has no organic input from the surface. No bat droppings, no plant material carried by water, no insects wandering in from outside. Everything alive inside it is sustained entirely by the chemical energy of the rock and water. It is, in the most literal sense, a self-contained world, a pocket of life that has been running its own independent experiment in biology for millions of years, with no knowledge of anything happening above. Fungi add another dimension to the cave ecosystem. In systems where organic material does reach the interior, carried by water or deposited by trogloxines, fungi are often the primary decomposers, breaking down that material into forms that bacteria and small invertebrates can use. Some cave fungi are bioluminescent, producing a faint cold light through a chemical reaction that requires no external energy source. In the dark of a cave, this light is occasionally visible, a dim bluish-green glow on a piece of decomposing wood, eerie and beautiful and entirely natural. The light serves no known purpose in the cave environment. It is likely a metabolic byproduct carried over from surface-dwelling ancestors for whom bioluminescence may have had a function that darkness has since made irrelevant. The interactions between cave organisms are often more intricate than they first appear. In cave pools, communities of microorganisms form biofilms, thin, layered structures on rock surfaces that function almost like tissues, with different species occupying different layers and performing different chemical roles. These biofilms are extraordinarily slow-growing. Some cave biofilms have been estimated to have been building for thousands of years. They are also extraordinarily sensitive. The warmth and oils from a single human hand pressed against a cave wall can disrupt a biofilm community that took centuries to establish. Among the most remarkable cave-adapted animals in the world is the cave beetle genus Leptoderus, first discovered in 1831 in the Postuna cave system of Slovenia, making it the first cave-adapted invertebrate ever formally described by science. Its body has been so thoroughly reorganized by cave life that it barely resembles its surface relatives. The head is elongated, the antennae dramatically lengthened, the eyes absent, the abdomen swollen into a barrel shape that may help regulate moisture. It moves slowly, feeds on fungus and organic debris, and has never been found outside a cave in its entire evolutionary history. It is one of the most studied cave animals in the world, and after nearly 2 centuries of research, scientists are still discovering new things about how it lives. The Texas blind salamander, found only in a single underground aquifer system beneath San Marcos in Texas, takes cave adaptation in a slightly different direction. It is entirely aquatic, entirely blind, and almost entirely transparent. The red of its gills and the pink of its internal organs are visible through its skin. It hunts by detecting the pressure waves created by small crustaceans moving through the water, striking with a speed that seems incongruous with the otherwise unhurried pace of cave life. Its entire known habitat fits within a geological formation roughly the size of a small city, and its population has never been large. It exists in a kind of extreme specificity, perfectly suited to one particular set of conditions in one particular place, with no ability to exist anywhere else. What cave ecosystems reveal, collectively, is that life's requirements are narrower than its possibilities. The requirements, energy, water, chemical stability, are modest enough to be met in conditions that seem, from the outside, completely inhospitable. The possibilities, given those requirements, are vast. Evolution does not need sunlight. It does not need warmth or abundance or open space. It needs time, and it needs the right chemistry. And given those two things, it will build something, some network of organisms feeding on one another and on the rock itself in whatever darkness it finds. The caves beneath the Earth's surface have been demonstrating this for hundreds of millions of years. Every blind fish, every pale crustacean, every bacterial film growing imperceptibly on a cave wall is evidence of the same patient principle. That life, once it finds a foothold, does not easily let go. There is a kind of construction happening in caves right now, has been happening for millions of years, that involves no architect, no blueprint, no intention of any kind. Water moves through rock, picks up dissolved minerals, and deposits them somewhere else. That is the entirety of the process. And yet, what it produces, given enough time and the right chemistry, are structures of such precise geometry and such quiet beauty that the first European explorers to encounter them underground sometimes refused to believe they were natural. They looked, to untrained eyes, like the work of something deliberate. The mineral responsible for most cave formations is calcite, crystalline calcium carbonate, the same compound that makes up limestone itself. The process is a kind of reversal. Slightly acidic water dissolves calcium carbonate from the rock as it passes through it, carrying the mineral in solution. When that water reaches a cave passage and is exposed to the cave's air that has a different concentration of carbon dioxide than the water does, a chemical shift occurs. Carbon dioxide escapes from the water becomes less acidic, and calcium carbonate can no longer remain dissolved. It precipitates out molecule by molecule and attaches itself to whatever surface the water is touching at that moment. If the water is hanging at the tip of a crack in a cave ceiling, the calcite builds downward. If it falls to the floor, it builds upward. If it does both for long enough, the two structures meet. A stalactite grows from the ceiling. The word comes from the Greek stalactos, meaning dripping, and the mechanism is exactly that. Water moving to the tip of the formation, depositing a thin ring of calcite, then falling before the next drop arrives to deposit another ring. Over time, these rings accumulate into a hollow tube, sometimes called a soda straw, which is the earliest stage of stalactite formation. Soda straws are extraordinarily fragile, thin as a finger, sometimes meters long, and liable to shatter if touched or if the airflow in the cave changes enough to dry them out. When a soda straw eventually becomes blocked or its water supply increases, calcite begins depositing on the outside of the tube as well, and the formation thickens into the solid, conical shape most people recognize. A stalagmite grows from the floor, built from the calcite deposited by water that has fallen from above. Because the water hits the floor and splashes slightly before spreading outward, stalagmites tend to be wider and more rounded at the top than stalactites, with a shape that curves rather than tapers. They are also generally more robust, less prone to breaking, capable of growing quite large before their own weight becomes a structural concern. The largest known stalagmite in the world stands in Cueva Martin Infierno in Cuba, rising approximately 67 meters from the cave floor. A tower of accumulated calcite built one. invisible layer at a time over hundreds of thousands of years. When a stalactite and a stalagmite grow toward each other long enough, they meet and fuse into a column, a single continuous structure connecting floor to ceiling. Columns are among the most visually striking features of any cave, particularly when they occur in groups, creating what appears to be a colonnade in an underground hall. Some columns are narrow and delicate, the product of two slender formations that happen to align over millennia. Others are massive, wider than a person could embrace, formed by the merger of substantial stalactites and stalagmites that have been growing since before human civilization existed. The growth rate of these formations varies considerably, depending on how much water moves through the system and how mineral-rich that water is. In caves with abundant water flow, stalactites can grow several centimeters per century, fast enough that changes become visible across a human lifetime. In dry caves or in passages where water infiltration is minimal, the same formation might grow a single millimeter per century, advancing so slowly that it seems, on any human timescale, to be doing nothing at all. Most cave formations fall somewhere between these extremes, growing at rates measured in millimeters per decade, patient accumulations that register the passing of time in a unit no clock has ever been built to measure. The color of cave formations is determined by the minerals and organic compounds that the water carries along with calcite. Pure calcite is white or transparent. Iron oxides produce shades of red, orange, and yellow, the warm tones that color many well-known cave formations. Manganese produces blacks and dark browns. Copper compounds can introduce greens and blues. Organic material filtered down from the soil above sometimes stains formations in subtle shades of tan and amber. A single stalactite can carry multiple colors in distinct bands, each band representing a period in the cave's hydrological history when the water chemistry was slightly different, a shift in the soil above, a change in rainfall patterns, a variation in the vegetation growing on the surface. The bands are a stratigraphic record, legible to those who know how to read them. The floor of a cave chamber is often as complex as its ceiling. Where water pools and slowly evaporates, it leaves behind thin crusts of calcite, cave rafts, sometimes called cave popcorn when they form in irregular knobby clusters on walls and floors. In pools that have remained stable for long periods, calcite can accumulate into rhinestone dams, low, curving walls of mineral deposit that form around the edges of pools and gradually raise the water level, creating terraced structures that look engineered, but are entirely the product of water chemistry seeking equilibrium. The rhinestone pools of Pamukkek in Turkey, though technically a surface travertine system rather than a cave, follow the same chemical logic and offer some sense of what similar formations look like at the scale visible to the naked eye. Cave pearls are another floor formation, and among the most geometrically surprising. They form in shallow pools where dripping water agitates a small nucleus, a grain of sand, a fragment of calcite, keeping it in constant slow rotation while calcite precipitates onto its surface. The rotation ensures that the mineral builds up evenly in all directions, producing a sphere. Some cave pearls are the size of a pea. Others grow to the size of a golf ball or larger over thousands of years of patient rotation. They are found in clusters, sitting in their shallow basins, perfectly round, perfectly smooth, and composed of the same calcium carbonate as the walls surrounding them. The cave making spheres from the same material, it makes everything else, simply because the conditions for it happen to be right. What unifies all these formations? The stalactites, the columns, the rhinestone dams, the pearls, is the same mechanism operating across wildly different conditions. Water, mineral, time. The variations in what results are not the product of different processes, but of different circumstances, different flow rates, different mineral concentrations, different temperatures, different geometries of drip and fall and pool. The cave does not choose what it builds. It only follows chemistry. And chemistry, given enough time and enough variation in conditions, turns out to be capable of nearly anything. Not all cave formations follow the logic of gravity. Most of what grows in caves grows downward or upward, pulled by the weight of water, guided by the reliable geometry of drip and fall. But there is a category of cave formation that ignores all of this entirely, growing sideways, curving back on itself, spiraling outward in directions that seem to have no relationship to any force that should be acting on them. These formations are called helictites, and they remain, even now, only partially understood. A helictite begins like any stalactite, a thin tube of calcite initiated by water seeping through a crack in the ceiling. But somewhere in its development, it deviates, it curves, it branches, it grows at an angle, then changes that angle without apparent reason, producing shapes that resemble coral or tangled wire, or the frozen gesture of something reaching in multiple directions at once. Some helictites are a few centimeters long. Others extend half a meter or more from the wall, defying gravity with a consistency that initially baffled researchers. Several explanations have been proposed. Impurities in the calcite crystal structure may cause it to grow asymmetrically, each new layer slightly offset from the last, accumulating into a curve over time. Tiny variations in air pressure or humidity within the cave may redirect growth incrementally. Fluid inclusions within the formation itself may exert capillary forces strong enough to override gravity at the small scales involved. Most researchers now believe that helictite growth is driven primarily by hydrostatic pressure, the pressure of water within the tube pushing outward in whichever direction the crystal structure offers least resistance. Gravity is not absent from this process, but it is outweighed by forces operating at a smaller scale. The result is a formation that looks impossible and is, in fact, simply responding to a different set of rules than the ones most cave formations follow. Cave moon milk is stranger still in appearance, though its origins are better understood. It is a soft, white, paste-like substance found coating cave walls in certain humid passages, smooth, slightly wet to the touch, with a texture that has been compared to cream cheese or fresh ricotta. Moon milk is composed of microscopic calcite crystals so fine that they never solidify into hard rock, remaining instead in a perpetually soft state. Bacteria are often found within moon milk deposits, and some researchers believe microbial activity plays a role in preventing the crystals from consolidating. Medieval Europeans believed moon milk had medicinal properties and collected it from cave walls to treat wounds and digestive ailments. Whether or not those treatments worked, the substance itself is real enough, a form of calcium carbonate that has never quite committed to becoming stone. Then there are the crystal caves, and among them, one that exceeds every other known example by a margin so large it reads at first as an error. The Cave of Crystals, discovered in 2000 beneath the Naka mine in Chihuahua, Mexico, contains selenite crystals, a form of gypsum of a size that has no parallel anywhere else on Earth. The largest crystals in the cave are approximately 12 meters long and weigh up to 55 metric tons. They are not formations that have grown incrementally from dripping water. They are single coherent crystals, translucent and pale, that formed over a period of roughly 500,000 years while the cave was completely submerged in mineral-rich water heated by a magma chamber below. The water temperature held steady at around 50 degrees Celsius, warm enough to keep the gypsum in a state where crystal growth was thermodynamically favored, and stable enough to allow that growth to continue uninterrupted for 500,000 years. When the Naka mine began pumping water from the lower levels in the 20th century, it accidentally drained the cave, exposing the crystals to air for the first time in their existence. Entering the Cave of Crystals requires a specialized suit because the air temperature reaches 58 degrees Celsius with nearly 100% humidity, conditions that cause heat exhaustion within minutes without protection. Even with a suit, researchers can work inside for only about 30 minutes at a time. The cave has never been open to the public, and its long-term future is uncertain. Once the mine ceases pumping operations, the cave will flood again, and the crystals will continue growing in the darkness, adding to their half-million-year accumulation at a rate no one alive today will be able to measure. There are other crystal caves. The Cave of Swords, also beneath Nika, contains smaller but still remarkable selenite formations. Ice caves in Iceland and Austria grow crystals of a different kind. Water ice forming intricate structures along cave walls each winter and melting partially each summer, regenerating season after season in cycles that make them simultaneously ancient and perpetually new. What all of these formations share: the helictites defying gravity, the moon milk never hardening, the crystals of Nika growing to a size that seems to belong to a different scale of reality, is the quality of exceeding expectation. A cave is already a space defined by what the surface world does not prepare you for. And yet within it, the formations go further still, past the already remarkable logic of stalactites and columns, into territory where the rules seem to have been quietly rewritten by chemistry and time working together in the dark, unobserved for longer than most things on this planet have existed. The oldest human art in the world is not in a museum. It is not hanging on a wall in a temperature-controlled gallery, behind glass, beneath careful lighting. It is deep inside a cave in southern France, painted on uneven limestone in the dark, by someone who carried fire underground and pressed pigment into rock with their fingers and the heel of their hand, and then left and never came back, and the image stayed exactly where they put it for 37,000 years. Humans and caves have a history that predates writing, predates agriculture, predates every institution and structure that contemporary life is built upon. For the earliest members of our species, and for the Neanderthals before them, caves offered something the open landscape could not: shelter that did not need to be built, a ceiling that did not require construction, walls that blocked wind without any effort on the part of the person standing inside them. In a world where every calorie spent on survival mattered, the cave was an extraordinary gift, a structure already finished, already standing, requiring only occupation. The evidence of that occupation is everywhere. Hearths of charred bone and ash, some of them more than 400,000 years old, mark where fires were built at cave entrances across Europe, Africa, and Asia. Middens, accumulated deposits of food remains, broken tools, and discarded material record what was eaten and how it was processed. The bones of large animals appear alongside scrapers and cutting tools, evidence of butchery carried out in firelight. Caves were not simply shelters from rain. They were workshops, kitchens, places where the practical work of staying alive was organized and repeated across generations. Some cave sites show evidence of continuous occupation stretching across tens of thousands of years. The same location used, abandoned, and reoccupied so many times that the layers of human activity stack up like geological strata, each one preserving a thin record of the people who were there. But the most extraordinary thing humans left in caves was not practical. It was not a tool or a food remain or a structure built for warmth. It was an image. The Chauvet Cave in the Ardèche region of southern France was discovered in 1994 by a team of 3 spelunkers who noticed cold air seeping from a narrow opening in a cliff face. Behind that opening, they found a passage that led to a series of chambers covering roughly 800 meters. And on the walls of those chambers, paintings of a quality and sophistication that immediately rewrote the accepted timeline of human artistic development. Lions, rhinoceroses, bears, horses, and mammoths, rendered in charcoal and ochre with a confidence of line that suggested not the tentative mark-making of early experimentation, but something already mature, already skilled, already aware of how to use the curvature of the rock surface to give a painted animal the illusion of movement and depth. The oldest images in Chauvet have been dated to approximately 36,000 years ago. The painters were fully modern humans, anatomically identical to anyone alive today, working in the deep interior of a cave by the light of torches. Lascaux, in the Dordogne, discovered in 1940 by 4 teenage boys following a dog into a hole in the ground, is younger, approximately 17,000 years old, but no less striking. Its Hall of the Bulls contains some of the largest prehistoric paintings known, including an auroch, an extinct ancestor of domestic cattle, depicted at nearly 5.5 meters in length. The paintings at Lascaux were executed with an understanding of perspective and proportion that was not supposed to exist in Paleolithic art. The animals overlap. They are shown in motion. They occupy the wall not as isolated symbols, but as a composition, a scene, almost a gathering of creatures arranged by someone who thought carefully about where each one should go. Altamira in northern Spain, first described to the scientific community in 1880, was so sophisticated that its initial discoverer, a local landowner named Marcelino Sanz de Sachuola, was accused of forgery. The bison painted on its ceiling, using the natural bulges and contours of the rock to create the impression of three-dimensional form, seemed too accomplished to be the work of prehistoric humans. It took decades of subsequent discovery at other sites for the academic consensus to accept that Altamira was genuine, that Paleolithic people had, in fact, been making art of this quality all along. What drew people so deep into caves to make these images remains genuinely open. The paintings are not at cave entrances, not in the zones of comfortable firelight where people lived and cooked and slept. They are in the interior, in passages that required crawling, in chambers that required carrying torches through long approaches, in spaces that a person could only reach through deliberate effort and some courage. The deep cave was not a comfortable place to work. It was cold, it was dark, it was acoustically strange. It required sustained commitment just to reach. Whatever the painters went there to do, it was not casual. Some researchers have proposed that the deep cave was a ritual space, a place set apart from ordinary life precisely because of its difficulty and its darkness, used for ceremonies whose meaning we can now only guess at. Handprints, both positive and negative, appear at many cave art sites. A hand pressed against the wall and painted around, leaving a silhouette or coated in pigment and pressed directly onto the surface. These are among the most immediate images in all of prehistoric art. A hand pressed against a cave wall 40,000 years ago and outlined in red ochre is in the most direct sense imaginable, a mark of presence, someone saying, with the simplest possible gesture, that they were here. Other evidence suggests the cave was not only a canvas, but a place of structured activity. Bone flutes have been found near painted chambers, suggesting music was part of whatever happened inside. The acoustic properties of many painted chambers are unusually resonant. The walls reflect and amplify sound in ways that the original occupants may have recognized and deliberately sought out. Some researchers have mapped cave art sites and found a correlation between the locations of paintings and the locations of maximum acoustic resonance within the cave, as though the painters chose their walls not only for their visual surface, but for the way they carried sound. The cave received the earliest marks the human hands ever made on any surface. It was the first gallery, the first temple, the first place set aside for something beyond the immediate demands of survival. Whatever meaning those painted animals carried for the people who made them, whether religious, narrative, ceremonial, or something with no modern equivalent, the images survived in darkness for tens of thousands of years, waiting in silence for someone to come back with a light. The history of that adaptation runs from ancient sanctuaries to modern military installations, and it reveals something consistent about why caves have never entirely lost their hold on human activity. They offer conditions that constructed spaces struggle to replicate. In the ancient world, the cave's most significant second life was religious. Across the Mediterranean and the Near East, natural cave openings were understood as thresholds, places where the surface world and whatever lay beneath it came into contact. The oracle at Delphi delivered her pronouncements above a chasm in the earth, and ancient sources described vapors rising from below that influenced her visions. Whether or not those vapors were real, the symbolism was deliberate. The cave mouth is a point of communication between the human and the divine. The underground is a source of knowledge inaccessible on the surface. The Greeks called the underworld a place reached by descent, and caves were its most literal entrance. In Crete, the Dictaean cave was venerated for centuries as the birthplace of Zeus. Votive offerings, small figurines, bronze objects, ceramic vessels have been recovered from its interior in enormous quantities, deposited by worshippers who climbed to the cave across rough terrain to leave something behind. The cave at Lascaux was painted. The cave at Dicte was filled. Both impulses, to mark and to offer, suggest that the cave interior was understood as a space where gestures carried particular weight, where the ordinary logic of the surface world was suspended. The early Christian tradition extended this logic in a different direction. Hermits and ascetics across the Middle East and North Africa withdrew into caves deliberately, seeking the isolation and sensory reduction of the underground as a condition for contemplation. The cave became a place of spiritual discipline, not sacred because of what it contained, but because of what it removed. Noise, distraction, social obligation, the ordinary texture of daily life. The cave stripped all of it away and left the person inside with nothing but silence and stone. The monasteries carved into the rock faces of Cappadocia in Turkey, and the cave churches cut into the cliffs of northern Ethiopia, developed from this same tradition. Communities of people who found, in the cave's natural architecture, a structure better suited to their purposes than anything they could have built. Secular use ran alongside the sacred throughout history. The stable temperature of cave interiors made them valuable for storage long before refrigeration existed. Wine cellars cut into limestone have been in continuous use across France for centuries. The caves of the Loire Valley and Champagne regions maintain temperatures and humidity, levels that no surface building can match without mechanical intervention. Cheese aging, mushroom cultivation, the curing of certain meats. All of these practices developed partly because caves provided conditions that were difficult or impossible to reproduce above ground. In times of conflict, caves became something else again. Their concealment, their multiple entrances, their resistance to conventional assault made them natural refuges and strategic assets. During the Second World War, caves across Europe, Asia, and the Pacific were used as weapons depots, command centers, field hospitals, and hiding places for cultural treasures. The Altamira cave in Spain was partially used for storage during the Spanish Civil War, its prehistoric paintings sharing space with the logistics of a modern conflict. In Vietnam, the Viet Cong developed elaborate tunnel and cave systems in the karst landscape of the north that proved extraordinarily difficult for conventionally equipped forces to locate or neutralize. The cave's oldest quality, its hiddenness, remained militarily relevant in the 20th century for the same reason it had been practically relevant in the Paleolithic. Prisons, too, found a natural expression in caves. In several medieval European cities, natural cave systems beneath urban areas were extended and adapted into holding cells, the rock providing walls that required no construction and that were essentially impossible to breach from the inside. The cave system beneath Nottingham Castle in England contains chambers that were used for this purpose, their walls still bearing the marks of centuries of occupation. The darkness and isolation that made caves appealing to hermits seeking contemplation made them equally effective as instruments of punishment. In the modern era, the cave has found new roles that its earliest occupants could not have anticipated. Underground cave systems are used to house data centers, where the stable temperature reduces cooling costs and the rock provides natural protection against surface events. Nuclear waste storage proposals frequently involve deep geological formations, using the same logic that kept prehistoric paintings intact for 37,000 years. That deep rock is among the most stable and isolated environments available. In Norway, the Svalbard Global Seed Vault is cut into permafrost rather than karst, but follows identical reasoning. The underground preserves what the surface cannot guarantee. Through every one of these transitions, from shelter to sanctuary, from sanctuary to cellar, from cellar to fortress, from fortress to archive, the cave itself has not changed. The same darkness, the same temperature, the same silence that made it useful to the first human who stepped inside still make it useful today. The applications have multiplied across millennia, but the underlying qualities that generate them have remained perfectly constant, waiting in the rock for whoever arrives next with a need the surface cannot meet. There is a mountain in central Vietnam, in a region of forested karst, so remote that local hunters avoided it for generations, where the ground opens without warning into a shaft so large that clouds form inside it. Not mist, not humidity, actual clouds moving slowly through a chamber whose ceiling rises high enough above the floor that weather becomes possible. The cave is called Hang Son Doong, which translates roughly as Mountain River Cave, and it was not known to the outside world until 1991, when a man named H. Can stumbled across its entrance while sheltering from rain in the jungle and was driven back by the roar of wind and rushing water from somewhere below. He could not find it again for nearly 2 decades. When he finally relocated the entrance in 2008 and guided a team of British cavers inside, what they found required an entirely new set of measurements to describe. Son Doong is the largest known cave passage in the world by volume. Its main chamber stretches approximately 5 kilometers in length, rises to a height of 200 meters in places, and reaches widths of 150 meters. A Boeing 747 could fly through it without touching the walls. The cave contains its own river, its own jungle, a forest of trees growing from the cave floor beneath 2 enormous dolines, collapsed sections of the ceiling through which sunlight enters and rain falls, and its own local weather system. The formations inside include some of the largest stalagmites ever recorded, rising over 80 meters from the cave floor, so tall they disappear into the mist above. Explorers on their first entry described the experience of walking through the cave's jungle section as genuinely disorienting. The presence of trees, birds, and insects inside what is technically an underground passage challenges every assumption about what a cave is supposed to be. Son Doong was fully surveyed only in 2009 and opened to a very limited number of guided visitors in 2013. The Vietnamese government has consistently resisted proposals to install cable cars or expand access, a decision that has preserved conditions inside the cave essentially unchanged from what H. Can first encountered. The jungle growing beneath the dolines is, by most measures, a primary forest, one that has never been logged or significantly disturbed by human activity, existing in its own sealed world beneath the mountains of Quang Binh Province. On the other side of the planet, in the hills of south-central Kentucky, lies a cave system of a completely different character. Not the tallest or the most visually dramatic, but the longest mapped cave in the world by a margin that no other system currently approaches. Mammoth Cave has over 650 kilometers of surveyed passage, and new sections continue to be mapped each year by teams working through the system's more remote corridors. The total extent of the system is unknown. Hydrological studies, tracing the path of water introduced at the surface and tracked until it emerges at springs, suggest that the connected passages may extend considerably beyond what has been physically entered and measured. Mammoth Cave has been known to humans for at least 5,000 years. Indigenous peoples of the region entered the cave extensively, leaving behind artifacts, footprints preserved in the soft clay of the cave floor, and the remains of torches made from cane and bark. Some of their explorations reached remarkable depths. Human remains have been found several kilometers from any entrance, in passages so narrow and so remote that the journey would have required sustained effort and considerable courage, even with modern equipment. In the early 19th century, the cave was mined for saltpeter, potassium nitrate, used in the manufacture of gunpowder during the War of 1812. Workers built wooden pipeline systems inside the cave to transport water for the mining operation, and sections of those pipelines are still visible today, preserved by the cave's stable, dry air. Lechuguilla Cave in New Mexico was, until 1986, considered a modest and unremarkable dead-end passage near Carlsbad Caverns. A persistent draft from the bottom of the known cave suggested there was more beyond, and a group of cavers spent several years digging through the rubble that blocked the passage. When they finally broke through, they found one of the most geologically significant caves ever discovered, a system of over 240 kilometers of surveyed passage filled with formations of a type and quality rarely seen elsewhere. Lechuguilla is a sulfuric acid cave, meaning it was not formed by the downward movement of slightly acidic rainwater, but by sulfuric acid rising from below, produced by the interaction of hydrogen sulfide gas with groundwater. This unusual chemistry produced an unusual cave. Its passages are lined with gypsum formations, chandeliers, sprays of crystals, delicate curved structures called cave pearls that are extraordinarily pristine because the cave has no surface water infiltration to disturb them. Lechuguilla is not open to the public. Access is restricted to permitted scientific researchers and experienced cavers working on survey projects, and the number of people allowed inside each year is deliberately kept small. This is partly to protect the formations, and partly because the cave contains microbial communities of unusual scientific interest, bacteria living in the rock walls that have been isolated from the surface for millions of years, and that produce compounds with potential antibiotic properties. Several novel bacterial species discovered in Lechuguilla have produced chemical compounds that are effective against drug-resistant pathogens, a finding that has made the cave of interest not only to geologists but to medical researchers looking for new pharmaceutical leads in unexpected places. The Blue Hole of Dahab in Egypt's Sinai Peninsula occupies a different category entirely. Not a terrestrial cave, but a submarine sinkhole, a vertical shaft dropping through coral reef into the floor of the Red Sea. Its entrance sits just offshore, accessible by walking across a shallow reef flat, and it drops approximately 130 meters to a sandy bottom. A horizontal tunnel called the Arch connects the shaft to open water at a depth of around 56 meters, deep, enough that reaching it on a single breath of compressed air requires careful planning and considerable experience. The Blue Hole has claimed more lives than almost any other dive site in the world, most of them experienced divers who underestimated the depth of the arch or succumbed to nitrogen narcosis, a disorienting, judgment-impairing effect of breathing compressed nitrogen at depth while attempting to navigate it. A memorial on the shore above records the names of those who did not return, and the list is long enough that the site carries a particular weight alongside its extraordinary beauty. What connects Sun Doong and Mammoth Cave and Lechuguilla and the Blue Hole is not simply scale, though scale is part of it. It is the quality of having exceeded what the people who first approached them expected to find. Each of these places was, at some point in recent history, either unknown or believed to be something smaller and simpler than it turned out to be. Each revealed itself gradually, requiring persistence and often years of effort before its true extent became apparent. The planet, it turns out, keeps its largest rooms well hidden, behind jungle entrances, beneath rubble blockages, under the surface of warm seas, and gives them up only to those patient enough to keep looking. Not all remarkable caves are made of limestone. Not all of them are dark. Not all of them are underground in the conventional sense, hidden beneath soil and rock, accessible only through narrow entrances in hillsides or cliff faces. Some of the most extraordinary cave environments on Earth form in ice, in volcanic rock, in the flooded limestone platforms beneath tropical seas, and they operate according to entirely different rules than the caves that most people picture when they hear the word. Cenotes are the most inhabited of these alternative cave worlds. Found primarily across the Yucatan Peninsula of Mexico, they are sinkholes formed where the roof of an underwater cave system has collapsed, creating an opening to the surface through which light enters and rainfall collects. The Yucatan sits atop one of the most extensive underwater cave networks in the world, a system called the System of Sac-Acton that stretches over 340 kilometers of surveyed passage and connects through flooded tunnels to dozens of surface openings across the peninsula. The Maya understood cenotes as sacred portals to Xibalba, the underworld, and used them for ritual purposes, including the deposition of offerings and, in some cases, human sacrifice. Archaeologists working in cenote systems have recovered jade, ceramic vessels, carved bone, and human remains from depths that required specialized diving equipment to reach, preserved in the cold, still water for over 1,000 years. For cave divers, the flooded passages connecting cenotes represent some of the most technically demanding environments in the world. The water is extraordinarily clear, filtered through limestone over decades, free of the suspended particles that cloud most surface water, giving visibility that can extend 30 meters or more in a single direction. The passages are often vast, with cathedral-like chambers opening unexpectedly from narrow tunnels. Their ceilings decorated with stalactites that formed when sea levels were lower and the caves were dry. Diving through these formations, through passages that were once open air, that once held the same slow drip of calcite water as any surface cave, is to move through compressed geological time, passing from one era to another within a single breath cycle. Lava tubes produce a different kind of cave entirely, and some of them are among the most visually distinctive underground environments on Earth. The Thurston Lava Tube in Hawaii, Volcanoes National Park, is short enough and well-lit enough to be walked through by casual visitors, its walls displaying the smooth, rippled texture left by flowing lava and the ledge lines that mark successive lava levels as the tube drained. But longer, more remote lava tubes on the same island system containers rarely seen elsewhere. Lava stalactites formed when molten rock dripped from the ceiling and cooled in place. Lava benches, and in some tubes, translucent mineral crusts of unusual color produced by the specific chemistry of volcanic rock. On the Canary Islands, the Jamios del Agua lava tube on Lanzarote descends to the coastline and opens, at its far end, into a brackish lagoon connected to the ocean through submerged passages in the rock. In this lagoon lives a blind albino crab, Nenitis scopularis, found nowhere else in the world, adapted to the specific conditions of a cave that is simultaneously volcanic, coastal, and aquatic. The lagoon has been incorporated into a cultural space designed by the artist and architect Cesar Manrique, who built an auditorium and garden within the tube itself, making Jamios del Agua one of the very few caves in the world that functions simultaneously as a geological site, a biological habitat, and a working concert venue. Ice caves introduce yet another dimension. The Eisriesenwald cave in the Austrian Alps, whose name translates as World of the Ice Giants, is the largest known ice cave in the world, containing over 40 kilometers of passage and ice formations that have been building and rebuilding for centuries. Unlike glacier caves, which exist within moving ice, Eisriesenwald is a limestone cave whose entrance geometry allows cold winter air to flow in and become trapped, while the warmer summer air cannot penetrate as deeply. Ice accumulates each winter and melts partially each summer, maintaining a dynamic equilibrium that has kept the cave's interior frozen for as long as records exist. The formations inside, ice columns, frozen waterfalls, vast dome chambers of blue-white ice, are not static. They shift slightly each year, responding to variations in winter temperature and snowfall, making the cave a slow-motion record of regional climate variation, as well as one of the most visually striking underground environments in Europe. What these caves share: the flooded cenote systems, the lava tubes opening to the sea, the ice caves rebuilding themselves each winter, is the quality of existing at a boundary. Each one sits at the edge of two environments: land and water, rock and ice, geology and ocean. They are transitional spaces, formed where one set of conditions meets another, and that boundary is precisely what makes them extraordinary. The most remarkable caves in the world are not always the deepest or the longest. They are the ones where the planet's different systems, water, ice, fire, time, have met and in meeting, made something that neither could have produced alone. The maps are incomplete. This is the first thing that serious cave researchers will tell you, and it is stated not as an admission of failure, but as a simple description of the current situation, one that has not changed meaningfully in decades, despite better equipment, better technology, and more people working on it than at any previous point in history. The cave systems of the Earth have not been fully explored, not even close. The passages that have been entered, surveyed, and mapped represent a fraction of what geophysical evidence suggests exists a surface. And every year, in mountain ranges and tropical karst plateaus and remote coastal cliffs on every inhabited continent, new cave entrances are found, and new systems begin to reveal themselves to the people, patient and skilled enough to follow them inward. In 2019, divers working in the flooded cave systems of the Yucatan connected two previously separate mapped systems, the Sac-Acton system and the Dos Hoyos system, confirming a continuous underwater passage that made the combined network the longest known underwater cave in the world at the time of its announcement. The connection had been suspected for years based on water chemistry and flow patterns, but physically locating and swimming through the link required months of preparation and multiple dive teams working from both ends simultaneously. What the connection revealed was not just a longer cave, but a more complete picture of how water moved through the entire Yucatan platform, information with direct implications for the water supply of millions of people living above it. In Papua New Guinea, cave systems in the remote highland karst remain almost entirely unsurveyed. The logistical difficulty of reaching them, requiring days of travel through dense jungle to access terrain that is itself technically demanding, means that many known entrances have never been entered beyond their initial chambers. Aerial and satellite surveys have identified karst formations across the region that almost certainly contain significant cave systems, but the gap between identification from above and actual exploration below remains wide. The same is true of parts of Borneo, of the Ethiopian highlands, of cave-bearing limestone formations in Central Asia that received almost no systematic attention during the 20th century and have seen only limited exploration since. What makes the unmapped cave significant is not merely its existence, but what it may contain. Cave archaeology has repeatedly demonstrated that the underground preserves material that the surface destroys. Bone, wood, fabric, pollen, ash organic material that would decompose within years on the surface can survive for tens of thousands of years. Inside a cave where temperature is stable, humidity is controlled, and the disruptions of weather, erosion, and biological activity are largely absent. The cave is, in archaeological terms, an extraordinarily conservative environment, one that keeps what it receives without significant alteration. The fossil record found in caves has rewritten human prehistory on multiple occasions. The discovery of Homo naledi in the Rising Star Cave system in South Africa in 2013, reached through a passage so narrow that the excavation team had to be selected partly on the basis of their ability to fit through a 18-centimeter gap, added entirely new species to the human family tree. The fossils were found in a remote chamber with no obvious natural means of entry for large animals, suggesting that Homo naledi may have deliberately placed its dead in the cave, a behavior previously considered exclusive to anatomically modern humans. Subsequent dating of the fossils placed them at between 200 and 300,000 years old, making them contemporaries of early Homo sapiens rather than distant predecessors. The cave had kept this information intact and inaccessible for 250,000 years, waiting for a team small enough and determined enough to reach it. In the Philippines, the Callao Cave yielded fossil remains in 2019 of a previously unknown hominin species named Homo luzonensis, identified from teeth and small foot bones recovered from a chamber that had been partially excavated in earlier decades without the finds being fully analyzed. The fossils suggested a small-bodied species with a mixture of primitive and modern anatomical features, living on the island of Luzon at least 67,000 years ago. The cave had been known and visited for decades. The species it contained was identified only when the existing material was re-examined with fresh analytical tools and closer attention. Cave sediments also preserve records that have no surface equivalent. Pollen trapped in cave deposits can reconstruct the vegetation history of a region across timescales far beyond what surface soils normally allow. Charcoal layers record fire events, whether from human activity or natural causes, with a precision of dating that sediment cores from lakes and bogs cannot always match. Animal bones accumulating in cave floors over thousands of years create faunal records that reveal not only which species were present, but when they arrived, when they disappeared, and how their populations changed in response to climate shifts and human pressure. The cave floor is a stratigraphic archive, and each layer, carefully excavated and analyzed, adds resolution to a picture that would otherwise remain blurred. The speleothem record, the climate information encoded in stalactites and stalagmites, has become one of the most valuable tools in paleoclimatology over the past 3 decades. The technique of analyzing oxygen isotope ratios within cave formations, developed and refined since the 1970s, allows researchers to reconstruct rainfall patterns, temperature variations, and monsoon intensity across periods extending hundreds of thousands of years into the past. A stalagmite from a cave in Belize might contain a detailed record of drought cycles that correlates precisely with periods of political instability and population collapse in lowland Maya civilization. A formation from a cave in Oman might preserve evidence of the weakening of the Indian Ocean monsoon at a moment that corresponds to the abandonment of early agricultural settlements in the region. The cave does not record human history directly, but it records the environmental conditions within which human history unfolded, and those records are often more precise and more complete than anything written sources can provide. There are caves that have never been entered, whose formations have been growing since before the first stone tools were made. There are passages whose floors have not been disturbed since the last ice age, whose sediments contain pollen from plant communities that no longer exist, whose walls may bear marks left by people whose names and languages are entirely lost. The cave keeps what it receives without judgment and without preference, holding the record of everything that has ever reached it: bone, pigment, pollen, mineral, water, in the same stable dark that received it, unchanged across whatever span of time has passed above. Science has spent centuries looking downward into caves and has only recently begun looking outward from them. The same qualities that make caves valuable to archaeologists and climatologists, their stability, their isolation, their resistance to the disruptions of the surface world, have made them interesting to a completely different field of inquiry: the search for life beyond Earth. Mars is not the barren, featureless world that early telescope observations suggested. Its surface is geologically complex, marked by ancient volcanic provinces, vast canyon systems, and most relevant to cave researchers, extensive lava tube formations visible from orbit. The Martian atmosphere is thin enough that the surface receives intense ultraviolet and cosmic radiation, making it hostile to any organic chemistry that might still be occurring on the planet. But beneath the surface, in the stable interior of a lava tube sealed from the atmosphere, conditions would be significantly more protected. Temperature fluctuations that swing wildly on the Martian surface would be buffered underground. Radiation levels would drop dramatically with even a meter of rock overhead. If liquid water exists anywhere on Mars in the present era, a question still actively investigated, the interior of a cave system is among the most plausible locations. NASA and the European Space Agency have both identified candidate lava tube entrances on Mars using orbital imaging, dark, roughly circular features called pit craters that appear to open into subsurface voids. On the Moon, similar features have been identified, and lunar lava tubes are now being considered as potential sites for future human habitation, precisely because they offer natural radiation shielding and thermal stability that no constructed surface structure could easily replicate. The cave, which sheltered the earliest humans from wind and predators, is being considered as shelter for the first humans to live beyond Earth. The logic has not changed. Only the location has. On Earth, caves have become important testing environments for the equipment and protocols that space agencies intend to deploy elsewhere. The European Space Agency runs a program called Caves Cooperative Adventure for valuing and exercising human behavior and performance, skills in which astronaut candidates spend extended periods living and working in cave systems in Sardinia. The program is not primarily about geology. It is about isolation, team dynamics, communication under conditions of sensory restriction, and the management of uncertainty in an environment where standard navigational references do not apply. The cave, it turns out, approximates the psychological conditions of space travel more closely than almost any other environment accessible on Earth. Closer to the surface, the conversation around cave conservation has grown considerably more urgent in recent decades. Cave ecosystems are extraordinarily vulnerable to disturbance. The white nose syndrome fungus, introduced to North American bat populations from Europe sometime around 2006, spread through cave systems across the continent with devastating speed, killing bat populations in some caves by more than 90%. Because bats are the primary energy input for many cave ecosystems, their droppings sustaining entire food webs of invertebrates, fungi, and microorganisms. The collapse of a bat colony can cascade through a cave's biology in ways that take generations to recover from, if recovery occurs at all. Human visitation, even well-intentioned visitation, carries its own risks. The carbon dioxide exhaled by tourists alters cave air chemistry. Body heat raises local temperatures. Introduced microorganisms carried on clothing, on skin, on the soles of boots, can colonize cave environments and outcompete communities that evolved in isolation over millions of years. The white nose fungus itself is believed to have been introduced to North American caves on the equipment of cavers who had previously visited European cave systems. Many of the world's most significant caves now require visitors to decontaminate equipment between sites, and access to scientifically sensitive areas is restricted to researchers who understand exactly what they are entering and what they risk bringing with them. The caves that remain unvisited are, in a sense, the most valuable of all. Every passage that has never been entered retains conditions that entered passages have already lost. Air chemistry unaltered by human breath, sediments undisturbed by human footsteps, microbial communities intact in whatever configuration thousands or millions of years of isolation have produced. These are not merely scenic resources. They are scientific ones, and their value increases precisely because so few comparable environments remain. There is something that resists easy articulation about what caves represent at this particular moment, when the surface of the planet is more mapped, more monitored, and more altered by human activity than at any previous point in history. The cave remains, in most of its extent, unmapped and unaltered. It continues to form, to preserve, to sustain life in the dark, operating on timescales that have nothing to do with the pace of anything happening above. It does not require acknowledgement. It does not change in response to being known or unknown, entered or left alone. Whatever the surface does next, the cave will continue. Water will move through limestone. Calcite will accumulate, one invisible layer at a time. Something pale and patient will drift through an underground river, sensing the world through pressure and vibration, indifferent to the light it has never needed. And somewhere, in a passage that no human has yet found, a formation will add another year to a growth that began before our species existed, recording, in the only language it knows, that time is still passing, that the planet is still working, and that there is still more beneath the surface than anyone has thought to look for.